Sorry about that. I meant to give you some a little bit more warning before I got cut off on the last video here. Chapter 2 is a little bit longer and more detail, and that's why it's requiring 2 videos for that. So I think the break actually came at a pretty natural point. We closed up on talking about stem and leaf plots and histograms and how they relate. Right now we're going to take a look at another graph, you might call it, and essentially it's called a box plot or a box and whisker plot. But before we can get into that, we need to have a dialogue and a conversation about percentiles and quartiles. So you'll see the slide right here, percentiles and quartiles given an observed value x in a data set. So x represents a specific value that we are evaluating within a data set. X is the pth percentile of the data if the percentage of the data that are less than or equal to x is p. So whatever the value of the data is, the percentage of it that is less than or equal to p, that would represent the percentile rank. So many of you know about the percentile rank, through taking the SATs, the PSATs, the ACTs. What percentile am I in as an individual? And that's what a percentile rank is, basically meaning that where you score at or below is that percentage. So if you were in the 90th percentile, then 90% of people are at or below you. That means only 10% are above you, okay? But that's how we calculate percentile rank. Percentiles and quartiles, for example, the percentile is the value 1.39 in the data set of 10 GPAs, okay? So 1.67, these are all written not in order, okay? So the first thing we need to do is put them in order from least to greatest. Then we need to find the values that are less than or equal to 1.39. So 1.39 itself is in the bottom portion here. It's only 1/10 of the data. So we can say since 1 is 1/10, which equals 0.10, there's 10 values of data, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this happens to be the first out of it, so that's why it's 1 divided by 10. We can say that 1.39 is in the 10th percentile. 8 data values are less than or equal to 3.33. So in that case, we can say that 3.33, this should actually be another bullet point here. Look at that. Sorry, I missed that. Since 8 is 8 out of 10 or 0.80, then we can say that 80% of 10, the value 3.3 is in the 80th percentile. Okay. Percentiles and quartiles. The 3 percentiles that cut the data in fourths are 3 quartiles. So basically we're breaking it into 4 sections. We have our outer 2 sections and then our inner 2 sections. Those inner 2 sections are very special. They're actually called the interquartile range. But those outer 2 sections represent the max and the min at the ends there, okay? The second quartile Q is in fact the median. So you have the median, which is right in the middle, okay? We have our minimum value. We have our maximum value. So this is quartile 1, okay? Actually, this is the the minimum value. This is quartile, so I'm sorry, let me say that again. This is the minimum value. This would be quartile 1, quartile 2, or the median value, quartile 3, and then our maximum value. And that breaks our data up into 4 quarters. And we see it listed out here in this sort of set here. But then as I talked to you about that inner portion between quartile 1 and quartile 3, if you take quartile 3 and you subtract from a quartile 1, what you get is the interquartile range. And then you have your max and mins out here. So we're going to see a little diagram in a bit. But before we do that, we're just bringing to this, and they're calculating what the second quartile is. You're calculating the third quartile. If there's 10 pieces of data here, you add, all right, the two in the middle together, which represent what our median is. So it's 2.62, add and divide by 2. Thus, the second quartile 6 is 2.62. Once you have that middle value, then you can go ahead and you can find the lower and the upper. So the lower and the upper. This would be the lower grouping. This would be the upper grouping. And know that the ends on that, so the 2.17 and the 2.53 is what you added together and divided by 2 in order to get the median value. And then we have our quartiles here. So based off of this, the first quartile is 1.90. It's the median of the lower group of values. That would be that set L that was on the previous slide. And quartile 3 would be the median of the upper group of values, okay? The interquartile range, obviously we're just taking Q3 and we're subtracting from it Q1, and that's going to get us our interquartile range. And basically all we talked about creates what we have. This is this box plot here. So this is your first grouping. This would be the lower grouping. This would be the upper grouping. And then this would be your interquartile range between Q1 and Q3. All right. Now this last part here, which is probably one of the most important things for us to cover, has to do with something called a z-score. And we calculate a z-score. We can only calculate a z-score once we know important pieces of information like the average or the mean and the standard deviation. Okay, so you can see here we're calculating a sample z-score, and then we're calculating a population z-score. The sample z-score uses the sample mean and the sample standard deviation, and the population z-score uses the population mean and the population standard deviation. And what does X represent? X simply represents a value in our data set. So when we're calculating the z-score, we're actually trying to find, well, what is the percentile? What is the percentile rank? What is the percent at or below a specific data point? So a z-score is a percentile, and that's what we just kind of talked about in the previous section here. Okay, so the formula and the definition allows us to compute the z-score. We're also going to use another chart that will help us to figure out what that percentage is, but we can't figure out the percentage until we first calculate the z-score. If the z-score is known, then X can be recovered using the corresponding inverse formula, right? So this inverse formula is just a manipulation of these formulas here to help us solve for X. That's all it is. Don't overcomplicate it. If z is negative, then X is below average. If z is 0, then X is equal to the average. And if z is positive, then X is above average, okay? Now, what we mean by that, all right, these are all values that are going to be between -1 and 1 that are going to help us to figure out exactly what percent is less than that particular data point. So an example here, find the z-score for 1.90. So 1.90 happens to be within this set. All we need to do is first put it in, well, yeah, I mean, we should really put it in order, but notice they don't really do that here. They figure out the sample mean and the sample standard deviation, and then what they do is they plug it into the formula. So this is our data value of 1.90. We subtract from that our sample mean, and then we divide it by our sample standard deviation. And what do we get? We get this value of negative 0.8589. That is our z-score, okay? So what I don't like in this particular case right now is I want to be able to take this and plug it into a chart. I don't have the chart for you right now because that chart's going to tell us what the percentage is. We're not going to worry about that at this point. Just know that this is the z-score and we're going to do something with that later. The last part that we need to talk about in this section is the empirical rule. And basically what the empirical rule relates to is what we would call standard normal data. Okay, now if we were to pick random data, the chances that that data would be normally distributed are pretty slim. But if we can say, and I'm going to say this again, we can only use these pieces of information here if we know beyond reasonable doubt that the data we have does represent what we would call a normal distribution. If the data is normally distributed, which represents a bell curve, I'm sure you've heard your teachers say, oh, the scores that you got on the test represent a bell curve, which means that the vast majority of you scored maybe in the C range. I had a very few that scored in the A range, a very few Fs, but we have some D's over here, we have some B's over here, but the majority are C's. That would be a normal bell curve distribution of data, okay? The empirical rule basically states this, and this chart explains it with these percentages here, but I'm going to go here. Basically, approximately 68% of the data will lie within one standard deviation of the mean. 95% of the data will lie within two standard deviations of the mean, and 99.7% of data will lie within three standard deviations of the mean. That basically means here, if you add or subtract one standard deviation from the mean, add or subtract two standard deviations from the mean, add or subtract three standard deviations from the mean, you will have this percentage of data. Notice it's almost 100%, but it's not 100%. It's 99.7%. This chart shows that a little bit more clearly. Notice 68% between one standard deviation from the mean, 95% two standard deviations from the mean, and 99.7% three standard deviations from the mean. This empirical rule chart, a standard normal table, we will use very frequently in this class, and you need to know it. So I would say some of the most important things that you need to pull from what we're doing right now is 1, the empirical rule, 2, understanding how to calculate a z-score, okay? And then 3, just knowing our simple understanding of mean, median, mode, range, being able to calculate the standard deviation or the variance. Okay. The empirical rule, data sets distributed must be approximately bell-shaped. This is what I said. It only applies when it's bell-shaped. It does not apply to data sets that are not symmetric and that are not bell-shaped. So that's important for you to know. Okay. And then we have Chevyshev's theorem. So this is very similar to the empirical rule, but what it's basically saying is that at least 3/4 of the data will lie within two standard deviations of the mean, 8/9 within three standard deviations of the mean, and this is almost 100%. That's what this basically is. It's almost 100% of the data lie with anything greater than that. Okay. All right, notice we're using the words at least here, so that's an important piece for you to understand. This data is not normally distributed, and that's what Chevyshev's theorem really focuses on. So the empirical rule is with normally distributed data, where Chevyshev's theorem is with not normally distributed data. And it's saying at least. So we can use Chevyshev's theorem when we don't know if the data is normally distributed, or if we can't say for sure, or if we just say that it isn't. It flat out is not normally distributed. Okay. A lot of key terms that we covered here that you're going to want to go over. Remember, I'm going to fly through these slides pretty quickly at the end. Okay. But these key terms are all available to you on the PowerPoint presentation for Chapter 2 that I shared with you, so you can go through it at your own pace. But then at the same time, you can also just watch my video of me explaining it. So, I'm just funneling through them. So this is, Chapter 2. Chapter 2 was covered in 2 videos. Chapter 1 was covered in 1 video. I just want to remind you that for this class, we are going to meet on Wednesday at 7 p.m. Posting this on Tuesday, so that would be tomorrow at 7 p.m. Okay? Hopefully you have a nice Tuesday, and we'll talk to you later.